Hello, fellow. My name is James Owusu-Appiah, and I believe in innovation and doing things differently. This video has been prepared for you to guide you through some well-known concepts that will aid your studies and preparations towards exam. Due to COVID, we cannot meet in person to discuss, so I hope this video finds you well and helps you achieve excellence. Thank you.
So now we to start executing the instruction, we'll make some few assumptions now. So in the first thing is that we assume that whenever the micro instruction, when the micro instruction counter is now at 0, right? When the content of that counter, right, is 0. We assume that at that instant, right, we don't have the instruction with us yet, so we have to kind of fetch, and then the fetch and decode stuff we have to do. So at this instant at 0. So let's focus first on the micro instruction counter. Okay, so let's bring the state first. So we are filling the table, right? So let's start filling in this table. Let's fill it in, and let me just try and separate the headers from the table itself. Let me try and separate the headers. You can see the difference. I'll try and just separate the headers and stuff from the table. Alright. So please try and follow, right? Just separating. This is just a comment, it's nothing. I want to just separate the headers from the table. So what we want to do is at this table, let's take so since we don't have the instruction yet, so we have to first fetch it. So we will just let me put a donk here and then permit him to use the underscore x, this underscore, right? This is just don't care. No matter what you use the x, that you don't care for something. Because for now we don't have the instruction at hand, so we just use we say we don't care or something like that, because the instructions are not yet at hand. So for this bits they are all for the current instruction, and then we don't have the current instruction now. So let's just set all of them into this thing underscore and just we are completing the table, so just keep these bars in lines, just a table. This thing then come to the micro instruction counter. Now let's focus on this counter aspect where we have 0 and it is now also have 0, right? And now for the feedback, we don't care for it, so let's keep this as I don't care now. And because we don't care now about the feedback. So the way we have written is as if this, okay, let's take this side for instance. The way we have written this is as if this mic 2 is for the low order bit, but that's not the case. This is the lowest order bit here. So let me try and do that to kind of flip that bit around. So I'll make this to be 3, 2, 1, 0. So yeah. So that we have our low order bits first, so that we can have the low order bits that way, and that way is going to work out. So let me do the same thing for this thing too. 3, 2. So I'm not changing anything, I'm just trying to reset the ordering of the bit. 3, no, not 3, sorry, this is 2, 1, 0. This is 2, 1, 0. So I'm constantly trying to rearrange the bits, right? So these are the low order bits, so they should come first. They should be there. So that's like how and the arrangement is I just want to put in a logical this thing, right? So normally when we're writing, we start writing the lower order bits there from right to left. So from right to left, right? So as you go this way, the bit order should be increasing. So, and that's how the schematic is like. So here, this 0 is the lowest order bit, followed by the 1, then followed by the 3, and then yeah, this. As you can see, this is the first lower order bit, the second, the third, and the fourth, like that. As you go here, the ordinary the bits order they are increasing, something like that. So we want to maintain the same order, something of that kind, the same order here. Also will affect our final result, right? So this is what we have now. we are at this 000, huh? We are at the 000 this state, and then we don't, because we don't have any instruction now, so we don't care about whatever is there, and then this two we don't have anything to. So now let's see, what do we want to do at the first this thing, because the first thing is that we don't have the instruction, so we have to fetch the instruction in the first place. So you see the micro instruction counter counts steps. Now we are at step 0, I mean, and at step 0, because we don't yet have the instruction, so obviously the only thing to do is to fetch the instruction. So how do you fetch an instruction? So let's see, how do you fetch an instruction? So to fetch an instruction, it's a matter of moving it from memory here, from the instruction memory, then putting it on the data bus. Then from there, we would like to kind of read that value into what the current instruction register. Have you seen it? So look at the steps. That is what we need to do to be able to fetch the instruction. So the first thing we need to do is what? So to get a value here that is in memory, right, to be able to output it here. Okay, okay, yeah, so let me still keep track of that, right? So let's take a look. Okay, so we want to what we want to do is that we want to like read a value from memory, right? So which location will we read the instruction from? So that is where the program counter comes into play. So the content of the program counter should we assume that it should be pointing, not even assume. At that instant, it will be pointing toward the next instruction to be executed. So we want to actually first fetch the content of the program counter, right? Put it on a data bus, and then from there we'll copy that value into what this instruction memory address register, right? Then once it's there, once the content of the program counter is in this register, then which means the current instruction will be visible on this line, right? So the next thing is to open this, to set this thing high so that this thing can be visible on the data line. Then from there we read it into what the current instruction register. So these are the steps to before we can be able to fetch the instruction. So let me come back to the systematic, right? The first thing is that the program counter always points to the next instruction, and now we are at step 0 and we don't have what? Any instruction. We don't have an instruction yet, so we have to fetch the instruction. So to fetch the instruction, we will output the content of the program counter to the data bus, right? And how do we do that? Well, the first thing we want to do is that we just have to set this control pin, right? This program counter output enable. We just have to set it high. That's all. So to output the content of the program counter to the data bus, we should set this signal high. That is it, and the buffer will be on, and the content will be on the data bus. So let's go and set the signal high. So let's look for PC. Now that's the way I have the table. So program counter output enable. Let's look for it here. So the program counter output enable. So let me come here. This is where the program counter output enable is, and hopefully let's hope that it does on this. So we will just set this bit to a high, to 1. I mean, we'll just set it to 1 because we are filling the table. So at the instant we'll set this to a 1 high, because now once you set this bit high, which means at that instant the content of the program counter will be available on the data bus. So now that we have the content of the program counter available on the data bus, so we would like to read it into the instruction memory address register. So basically what we want to do is we want to enable the input enable, right? We want to kind of be able to load it. So we'll set the signal high so that the register cannot be active and waiting for the clock to be able to execute that. So let's set the signal high too, because we want to read what is on the data bus into this register. But before we can write to the register, we have to first enable it. We have to make it so we enable it by making it high, where these are all active high this thing. So we will activate the signal, which is the instruction memory address register, input enable, so the IE. So let's look for that signal. So that's how it's good to label your signal. So that's and this way this signal is here. So let's go and label it there. Let's go and label this signal. Let's just label this signal, right? And so let's label the signal, and we will just call it we'll call it okay, let's not label it, I mean set it high, activate the signal. So we'll set the signal high, right? So we'll set that signal high. And then the thing is that once we have set the signal high, so I understand that the signal, the input enable is high. The content of the program counter is in the data bus, but it has not yet been read into the instruction memory address register. It has not yet been read into this register. We have to wait for the clock before it can happen. So one thing that happens is that because our next action, right, our next this thing depend on the result of our current operation, our next operation. So whenever our next operation depends on the result of our current operation, we have to wait for the clock. So that's it. So we have to wait for the clock. And then, so what it means is that we will wait for the clock, and then we will have to wait for the clock, right? And by doing that, so you see this thing happened okay. So we are now at 0, right? So we have to wait for the clock. And then when the clock rises, so we set our signals here. They are all on. They are active. They are high. The content said this is ready. So we wait for the clock. On the rising edge of the clock, then whatever is on the because this is high, and so whatever is on this data line will be what stored into what this register, right? And then once the clock rises, when it's falling, because this is for falling, because we have negated this signal that is going here. When it's falling, then it will be like a rising edge to this micro instruction counter. So it's going to increment to the next because that's what counter does. It's going to increment to the next. So first of all, let's activate. Let's keep it high. Sorry, let me show you something here. I want to kind of work on something. So somebody is playing. Yeah, don't forget, and you have to reset them because see, we want to keep this one always high. The counting level, right? Because normally before a counter can increment to the next, this signal must be high. Must be what, like high, before you can be able to count to the next distance, right? So that's why we'll just tie this into a high, or normally you say you tie it to a VCC or something. So we'll tie it to a high. Let me change that bit value to a 1. So we'll tie the signal to high. So the changes are important, but anyway, you have access to the final distance, so you will see all those changes there. Some of those changes they are not in a first part 2 circuit. So you see this we have tied high. So because the micro instruction counter is always the count enable signal is always what high. So which means whenever the clock is, and then we are negated the clock input. So whenever the clock is falling, it will see a rising edge. So whenever the clock is falling, it will increment automatically to the next value. So that is what will happen, right? So let me come back again and say one more thing. So we have activated the program counter output enable. The signal is high, so the content is in the data bus, and we also set the input enable of this one high, so the content was so it was ready. It was waiting for the clock to be able to store anything that is on this line. So yeah, so on the rising edge of the clock, we expect that this should be stored, right? Everything else should be stored. Then what will happen on the falling edge? On the falling edge, this micro instruction counter, because it has a negative clock input, it will see a rising edge, and then it will increment to the next step. So let me just